Hi guys. We are going to be, for the next few days, working on a engineering design project that will go kind of end our chemistry unit for now. We are going to, after this one, we're going to be talking more about the engineering and design process. So I kind of want to go over that with you just really quick by showing you a couple images here. This first one, if you Google engineering design process, you're going to find all kinds of different diagrams to kind of show this. And it's very much along the same lines as the scientific method, but it has to do with creating things, not necessarily making a hypothesis about the outcome of something. Okay, it's about what's your idea and how can we create it. Okay, so the first part of it is asking yourself the questions. What is the goal? What is it that you want to make? What is it that you are being asked to make? Then you're going to imagine what it could look like. You're going to explore what it could look like. You're going to do some research. You're going to figure out kind of what your object is going to look like. You'll design it with careful diagrams, labeled, taking careful notes and measurements. You'll make a prototype, which is making a kind of a test model. You'll test it, and then afterwards you can evaluate. Well, after this isn't really the end, nor is this really the beginning. Many times, just like in the scientific method, this will cause you to go back to the design process and make a prototype and test it. And in engineering, especially, it is very important that you don't ever get to the test and then end. This process here of going back and redesigning and refiguring and retesting and rebuilding is constant with engineers, okay? It is an ongoing process, and it is all about staying with the problem, okay? You have to stick with it. And it was told to me once by Miss Benjamin that if you say you can't, then you should end that statement with the word yet. I can't get it to work yet. Meaning it's just always a matter of a little bit of a tweak in your design in order to make it work. Okay? So to start with, we're going to do a fairly simple little project that kind of ties in some of the chemistry that we've learned. All right? So follow along with me. It says, imagine that you volunteered to rescue reptiles, turtles, snakes, and lizards, and that you are in the unlucky position of living in the path of new construction. Typically, in these cases, animals move. They search for new homes and food sources nearby. However, eggs cannot crawl, right? They don't have any feet yet. They cannot slither, and they cannot swim to another location, and the construction projects will not wait for the eggs to hatch. You've talked with the construction workers and with a nearby reptile conservation center. The workers are willing to notify you when they come across reptile eggs. The center is able to incubate the eggs or keep them warm until the babies hatch and then return them to the wild. Your role is going to be to design a reptile egg incubation device that will keep an egg warm and safe as it is transported from the work site to the reptile conservation center. Okay, so you have to make something that will keep an egg at a very specific temperature. Reptile eggs are leathery and soft. While they are not prone to crack easily, they need to remain in the same orientation they were originally laid. Okay, so however the egg came out of mama, it's got to stay in that same up-down position. It can't wobble around, it can't spin around. I'm not quite sure what that does to the critter inside, but I'm sure it's awfully confusing. Whatever is facing up must stay facing up. It cannot be flipped, turned, or jostled in any way. Very importantly, the eggs must be kept warm, but not too warm, to properly develop and hatch. You don't want to have a reptile omelet in your little incubator by the time you get to the conservation center, right? You're not making breakfast, you're saving reptiles. You have a job to do before the first batch of eggs is found. Build a temporary portable reptile egg incubator device that will keep one egg warm and properly positioned while you take it to the Reptile Conservation Center. Give these young lizards, turtles, and snakes their best chance at life. All right. So that's the background of the project that we're doing. Now, if you're a distance learner, you might be freaking out like, I don't know how to do something like that. And you're not going to have the chemicals to be mixing to make something of perfect temperature. That's okay. I'm going to do all of these steps with you on video. And so you can answer the questions that go along in this lab just by watching what I'm doing. All right. And I'll have a Google document for you to answer all of your questions on. All right. Okay, so it says the inspiration for an invention can come from just about anywhere. Sometimes it can come from products that already exist. Okay, so over here we've got an instant hot pack. Here's some hand warmers. I think this might be a cold pack. Oh no, this is a hot pack as well. Okay, we're going to watch a little video about these four things and learn about what makes them room temperature when they're just sitting there on your counter to warming up.
Here are 3 heat packs that each use chemistry in a different way to warm up. This heat pack contains a fine iron powder, a little bit of water, and some salt. The way it works is you remove it from this plastic wrapper, and the little packet that's inside, that's what contains the iron powder and the other ingredients. And it's covered by a porous outer covering so that air can come in. And what happens is the air, oxygen in the air, interacts with the iron, and there's a rusting reaction takes place. And that reaction is exothermic, and so it releases heat. So let's just take a look. Right now, this temperature is about 22 degrees. I'm going to put it under here. You're actually supposed to shake this packet up a little bit to activate it more or let more oxygen reach the iron. And then let's just check the temperature. It started at about 22 degrees, and we'll check it after about 5 minutes or so to see where we are. So this is about 5 minutes after we started, and it has gone up from about 22 degrees to almost 30 degrees. So it's kind of gradual, but it is increasing in temperature. Let's check one more time after maybe 15 more minutes has passed. So it'll be about 20 minutes of total warming up time. So this is after a total of about 20 minutes. We started at about 22 degrees centigrade, which is about 70 Fahrenheit, and we're all the way up to about maybe 43 degrees centigrade, which is almost 110 degrees Fahrenheit. So it's a gradual warmer, but it does get warm, and it stays warm for a long time. Okay, this type of heat pack contains a very concentrated solution of a chemical called sodium acetate. It also has a little metal coin in there, which you bend in order to activate the heat pack. So let me try that. And what happens is the solution crystallizes, and that process is very exothermic or heat producing. If you notice, I'll move it a little bit here, this heats up pretty quickly. It started at about 20 degrees. It's already up to about 40 centigrade. I'll come out a little bit. So this one heats up a lot more quickly than the first one that we saw, the hand warmer that was based on rusting. And it's already in just like 2 minutes up to almost the same temperature the other one was up to in 20 minutes. This heat pack contains a chemical called magnesium sulfate. And it also has a little pouch of water on the inside. The way you activate it is you have to push down and break that pouch of water. It's just not that easy to do. Then shake it up a little bit. And then it's the dissolving process that in this case is exothermic. It's heat producing. So this started at about 20 degrees or so. And we'll just leave it here and see how fast it warms up and by how much. So we're already at about 32 or maybe 34. I'll move it down just a little bit so we can see it better. It's already past 40. And so this will warm up, and probably it's definitely faster than the one with the iron filings, but it probably doesn't warm up as fast as the crystallization one. But just like the other two, it's another process that's exothermic.
Okie doke. Let's go back here. It says, what features of the 3 hot packs shown in the video keep them from getting hot before you want them to? Okay, so when you answer this question, make sure you are thinking of all 3, okay? What mechanism kept this from getting warm when it's just sitting there? What kept this from getting warm? Or what did you have to do to make this get warm? What did you have to do here? What did you have to do here? Okay, so there should be 3 different things listed for number 1 here. Number 2 and 3, the features that the device must have are called criteria. As you begin to think about a temporary portable reptile egg incubator, what features might be useful to borrow from the design of these hot packs? Okay, well, what does criteria mean? Criteria and constraints are 2 things that we will be talking about a lot when we're doing our engineering unit. Criteria are goals which must be met in order to satisfy a challenge. Okay, so for us, it needs to be portable, right? It has to keep the egg upright. Maybe it has to reach a certain temperature. There's all kinds of different criteria, goals that you have in mind when you're going to design. And then constraints are factors that limit how you can solve a problem. All right, so you might not be able to build something out of, metal and weld it together. I hope you're not doing that in my classroom. Maybe you don't have all the money in the world. Maybe, there's a bunch of different things that can limit as well. And the best way to make a good design is to have a really clear idea of what the goals are, what the criteria are, what things need to be met, and then also have a realistic idea of what your constraints are. All right? This question asks what features might be useful to borrow from the design of those hot packs. What are some of the ideas from those 3 hot packs that might come into play when you are making an incubator for an egg? And then number 3 says possible problems that might prevent the design from successfully meeting all the criteria are called constraints. Possible problems. It's like you're predicting there to be some issues, and there usually is. In an engineering and design process, when you are designing and building something, there are problems that come up. It's best to just plan for them as best you can. So what are some possible constraints or challenges which would prevent you from getting the features you listed above? Okay, so if you are going to be building an incubator, what are some things that you might not be able to get your hands on? What are some things down here that are unrealistic pieces of material that you would need to have up here? What are some constraints? What are you working against? I'll tell you right now, one of them is money. You are going to get very cheap materials from me to build this. So one of the constraints is money. You're not going to be able to say, okay, Miss Coda, I have an idea for an egg incubator, and what I need is 4 sheets of solid gold and a welding machine and a motorized cart. Yeah, no, that's not happening. So money is one. And then you can list some other things that might trip you up from making the dream one, the one that you might imagine in your wildest dreams. There are constraints there, right? It's not your wildest dreams of what this might be are not necessarily realistic. And so those are the constraints that you'll list here. Okay. The next part we are going to do the next day. All right. So this is all for today, just those first 3 questions, and I will talk to you soon.